Okay, I guess you got the type of questions what I'm talking about here, right? See, it can be this ketone and the Grignard can be this guy, correct? It can be this ketone and the Grignard can be this guy. I think you got the third one as well, right? It can be this ketone and the Grignard can be this guy. Tell me what's the fourth option that we have. No one? I got only one answer. No, Nandita, not that one. Try again. Guys, at least try. What gives you 3-degree alcohol? In Grignard, you learned it, guys. Which reaction gives you 3-degree alcohol? The fourth kind, I'm saying, like there are more possibilities than four actually, which I have just figured out. So if you have an ester, let's say, guys, you have an ester. From there also you can get a 3-degree alcohol by reacting 2 times with Grignard, correct? So now in one time you'd be using this Grignard, second time you'd be using this Grignard. Then also we can get a 3-degree alcohol. So this is the kind of questions, guys, you should be practicing for Grignard systems. Okay. Exactly, Shani. Now, this is one. Similarly, guys, make sure you can do the same things for aldol reactions, for Cannizzaro reactions as well. From the products, you know how to figure out the reactants. Okay, it's like you just have to pay a little bit of attention to figure that out. Okay, I'm not teaching you organic today. Today, my topic is completely, teaching about DNA block and coordination compounds. I do understand, guys, these two chapters are very, very simple because the questions are going to be very straightforward, but still I want to emphasize on some of the topics to you. Along with that, guys, I have prepared the last 10 years all the important questions which have been coming. I have made a PDF of all of those things. I believe if you just read those PDF of DNA block and coordination compounds, there isn't any question that you would find unknown to you. And it's not like there's a lot of questions in there, guys. I'm just keeping for DNA block, I guess total number of questions was 30. So I'm just posting 30 questions, combining, the short questions, MCQ questions, and the long questions. So combining them, it is 30. Similarly for coordination compounds as well. So only, even less than that. In coordination compound, I have only, 15 to 20 questions. If you just go through those questions, I am 100% sure, guys, every single question in the paper would be common to you. All right. And I'll be sharing those, PDFs with you as well. Now, right now, the same thing is, guys, I guess you have seen the topics as well. Similarly, I'm gonna give you a PDF of ABCD type questions, all right, which is known as the blackboard questions. So that those two webinars are gonna happen tomorrow, right? Today you have two webinars, I guess you have noticed that. So right now there is one and there is another one in the evening, correct? So today we'll be starting with the coordination and the DNA block question, guys. Coordination chemistry, I guess you are finding it a little bit comfortable in there. So the first question that you see over here, describe the shape and magnetic behavior. See, the question is just a normal question that I'm showing you, but guys, these kind of questions are 100% going to be there in your paper. Okay, one question from magnetic behavior and shape. So I guess all of you would be able to solve this particular question over here, guys. When you write it, when you represent this question, okay, that is something another very important thing, guys. I guess you can solve the question, but again, focus on the representation here. When you represent it, make sure you write every single thing here. Okay, so starting from, you do write the first. Let's solve the question number 1 here quickly. So cobalt is in 3 plus oxidation state, so don't write CO3 plus at one go. Write the oxidations, write the electronic configuration of cobalt first. Okay, make sure, guys, you write the nearest noble gas before it. I guess you guys are more comfortable in writing only 3d74s2, but make sure you're writing argon 18 3d74s2. They're just gonna find some place to cut your marks, guys, the moment your score goes beyond 90. They will just try to figure something out to cut your marks. So make sure that you don't give them any scope, right? So write this thing. After that, you write CO3 plus. Okay, argon 18 3d6, After you write it, do show them with the boxes, right? So 3D, 4S, 4P. Now ammonia. Make sure guys you write ammonia is a weak ligand, or you can also write borderline ligand, It's the best thing is borderline ligand, but just check it in the NCERT once. If it is written as borderline ligand, guys, in the NCERT, if it is written, then it's well and good. If it's not written, then just write it as weak ligand. Okay. Generally, ammonia is a borderline ligand. You all know that, right? So then, guys, just put the electrons in here. 1, 2, 3, 4, 5, 6. First, write in this way. Then you write like this: in presence of ammonia. In presence of ammonia. Then you write the coordinated part. Okay. Okay. So 1, 2, 3, 4, 5, 6. This is ammonia electrons, right? This is d orbital. Then make sure, guys, you put arrows like this. And because this is coordination bonding, make sure you write ammonia.
Sir,
Mm-hmm.
sir, isn't there something like in the presence of cobalt or like some other metal, ammonia acts like strong
100%.
ligand?
Exactly. In presence of cobalt in +3 state, ammonia does act like a strong ligand. It's a borderline ligand, right? But the point is, I don't think so. This concept is there in your NCERT. Just check this once. I guess this is something I have discussed in the coordination compounds, like the previous year question papers when I was discussing as well. Ammonia is actually a borderline ligand. Okay. With 3D metals, it does act like a weak field ligand when they are in +2 oxidation state. When they are in +3 oxidation state, ammonia acts like a strong field ligand. All right.
Yes, sir.
So cobalt specifically it acts like a strong field ligand. And one more thing, I have mentioned this as well. CO3 plus with this, only these following ligands are weak field. F minus, SCN minus, Cl minus, Br minus, I minus, all the halogens, SO4 2 minus, S2O3 2 minus. Other than these ligands, every single ligand with CO3 plus is strong field. This is the real concept behind it. But then again, guys, you just check what is written in the NCERT. According to
So, sir,
this concept, it should be pairing up. Yeah.
in this question, we use a strong ligand or weak ligand?
That is what I was mentioned. No? I mentioned that to you in the beginning only. First, you check that in the NCERT that NH3, how is it represented? Because for JE, we do teach this. For JE, we do teach that ammonia is a borderline ligand, and with 3D, for 4D and 5D, it is always strong field ligand. It is always strong field ligand for 4D and 5D. For 3D,
Yes.
for +2, it is weak field, and for +3, it is strong field. This is all known for you have learned it in the JE classes, right? But I
Yes.
just want you to look into your NCERT once. Are they writing MSC as a borderline ligand or a weak field ligand? Because in NCERT, as far as I remember, they are writing it as a weak field ligand. And that's how they have solved all the questions as well. That's why I'm showing you in this way. Just do one thing. Okay, I'll be sending you a message right after the session is over. I'll be checking in the NCERT as well. You do check it in the NCERT as well. Okay, and
Okay,
get
sir.
it confirmed in there.
Yes,
Okay,
sir.
other than that, just look at the representation here. So this is how you're going to write, and after that only you write the sp3d2. Right after you have written the hybridization, guys, save some time for the structure as well. It won't be taking long, but just draw the structure over there. Okay, so I guess that is it for nickel cyanide 4. I guess, guys, you can clearly understand whenever it's a strong field ligand. See, sometimes you can understand before you solve the question, right? As it is a strong field ligand, you know that, and the coordination number is also 4, so you can understand it's going to be DSP2. Correct? It's going to be your square planar structure. So just solve the questions. This question has been asked in 2010 CBSE, but guys, it has been repeated in 2017 and 2015 as well. So we can expect these kind of questions 100% to come. This exact question got repeated. Now you can clearly expect these kind of questions coming in this year as well. It's a must come kind of questions, guys. Okay. Now, let's go for this question. This question I have taken, guys, in order to teach you this part, because this particular question can be described in two different methods. Okay, so let's just read the question first. So, how is the stability of coordination compounds in solution decided? So, guys, when they say in solution, when they say in solution, then you are supposed to write in with respect to the stability constant. Stability constant. In solution, you write it as stability constant. Now, what is the stability constant here? So, let's say there is a metal. This is how you are going to represent it, guys. There is a metal with N plus oxidation state, and it is reacting with 6 ligand, 6L. I mean, I should write it as 6L like this. Then what is the coordination compound it would make? ML6 N plus, something like this, right? Now, guys, what would be the rate constant for this equation? It would be ML6 N plus divided by Mn plus L to the power 6. Correct? This particular rate constant is called, guys, the stability constant of a coordination compound. Okay. When the value of K is high, when the stability, by the way, it is sometimes written as beta as well, guys. Okay. So they can write this thing as beta 6 because there are 6 ligands. No? So they can write as beta 6. That means 6 ligand stability constant. Okay. So when this question comes in this way, beta 6. So you are going to explain like this is our rate constant for this equation. So when the value of beta 6 is high, that means my coordination compound is more stable. All right. So with respect to stability constant, you have to describe this thing. I guess, guys, you have learned about effective atomic number rule, EAN rule. As far as I remember, guys, the EAN rule is not discussed in the NCR. So you cannot use the EAN rule as well in here. Okay. EAN rule is only for your JE preparation. So I would suggest you to definitely JE and NEET preparation. I would suggest you to definitely look into the things, the explanations that you are used to giving. Are they there in the NCRT or not? Right? So here, whenever the stability question comes, guys, you have to explain with respect to beta. There is one way of solving this question. There is another way. So the other way is, always remember, this is something I have taught you in the sessions, guys. Always remember this. Whenever you have chelating ligand, they are stable, correct? Now, this is what people are going to write, but you are going to write they are stable because of, like, you're going to write like stable thermodynamically, right? Do use this word, guys, if this question comes. It is stable thermodynamically. I have taught you, if you remember, how the delta S becomes positive when you undergoes a reaction as phosphorylation, right? So I guess you do remember that. Sir, in NCRT, they have. Great, great. Okay, so according to Shreya is saying in NCRT, there is an example where they have paired ammonia up. So guys, then all the confusions are over. So you are gonna pair it up. For ammonia, you are gonna use it as strong field ligand. So just know this. Whenever it is cobalt in +3 state, guys, only these are the weak field ligands. Okay, it's not mentioned in the NCRT, but this is how it is. These are the weak field ligands there. So now Shreya is saying that she has found that in the book that they have paired it up. So guys, definitely you go ahead and pair it up as well. Correct? So you are gonna call it D2sp3 in that case. All right. 1, 2, 3, 4, 5, 6. So you're gonna call it D2sp3. So, and for your knowledge, guys, for your information, ammonia is strong field ligand for +3 oxidation states. For every D block elements +3 oxidation state, it's a strong field ligand. For +2 oxidation state, it acts like a weak field ligand. And for 4D and 5D series element, it is always strong field ligand. Okay, there is no such thing about oxidation states in here anymore. Okay, so it's always strong. All right, Bhavna. Yes, Sashank, I'll be sending all the PDFs. Don't worry. All right, guys. And do check that as well, Shreya. Are they calling it a borderline ligand or a strong free ligand? Like, what is the exact term that they are using? In actually, it's a borderline ligand, but just check that what is the term they're using. Okay, guys, I'm leaving this thing on you. Now, here, what was I saying? Right. Now, look at the second question. How is the dissociation constant of a complex defined? So, now you're going to write like this. Whatever is the stability constant, the reciprocal of that is called dissociation constant. So, it is the reciprocal of beta 6. So, that means the value would be mn plus L6 divided by, sorry, L to the power 6 divided by ML6. The PDF that I'll be sharing with you guys, that comes with a solution. So the questions and the solutions, all of those things are there. Okay, don't worry about that. Now, this is also done for the complex FeEN2Cl2. En is the diamine, the oxidation number of the iron, the hybridization. Okay, guys, quickly solve this question. What is the oxidation number of iron here? They're very simple questions in here. And make sure, guys, you are drawing the structure. You know how to draw the structures. Make sure that you write the ethylene diamine in the way they are. I've seen people losing marks for this. There are some of you, those who are comfortable in writing ethylene diamine like this, right? Don't do that in exam. Do it in the proper way. Correct? Now, what is the oxidation number of iron over here, guys? Quickly. Unexpectedly, I got only one answer. Come on, I think you're better than that, guys. Be quick. All right, don't worry about this ammonia thing, guys. I would just check the NCRT and just confirm that over the WhatsApp to you. Okay, don't worry about this ammonia concept. Okay, what is the iron coming, guys? Iron would be +2, correct? Ethylene diamine. Okay, there is one more thing I think I have told you in the class, guys. When you pronounce the name, when you go for the name, over there, is it coming +3? Oh, okay, there is a Cl in here, now they're putting comma. I guess that is the printing mistake here. Just one second. So it's an entire compound, guys. Okay. So whenever you are pronouncing the name, guys, there only you can understand the name ends with amine, right? If it's an anionic ligand, it would be ending with ate, ite, or ite, correct? So it would be +3 in that case, correct? The hybrid orbitals of the shape of the orbital. So guys, here also I guess you can understand the hybridization, the shape, the magnetic behavior. Magnetic behavior would be root over of n into n+2, correct? Now, there is another kind of question that they ask. They give you the new value, means the magnetic value, and they're asking you how many unpaired electrons are there. So let me give you guys the magnetic value they are giving is 4.92. Tell me how many unpaired electrons are there? How would you solve this question? Exactly, Nandita. So it's like, exactly. So the number that you see on the beginning, guys, that is the number of the unpaired electrons. Correct? So for 1, you would be able to see the value is coming as 1.78. For 2, it will be coming as 2.8 or something. For 3 unpaired electrons, the magnetic moment would be coming as 3.9 or something. Okay. So whatever the number of unpaired electron is the number before the decimal point. Okay. You can just use this shortcut. Okay. Now, right. Guys, quickly solve this question and tell me what is the answer coming. The molecular shape of NiCO4. What is the hybridization? Just tell me the hybridization here. So you can see that this is a strong field ligand, correct? So strong field ligand means we know the shortcut, it would be DSP2, correct? Right? Whenever we have a strong field ligand, it would be DSP2, it would be square planar. Any doubts, guys? Come on, write it down. Very good, Tejas. Let's see. Tejas is the only one so far who has written the right answer. Really, guys, you don't have any doubts? Right, Arav? Right, Aditya? Guys, this is the trick question. Okay, don't use the shortcut for this question here. It is not DSP2. It is SP3. Generally, when you solve questions of nickel, it is in +2 oxidation state. Like this guy. This is DSP2. But this nickel is in 0 oxidation state, guys. So it's not going to be DSP2. You can just look into it. Yeah, I would be solving the previous question as well. So nickel is in 0 oxidation state. So it is 3D8 4s2. Correct? So 3D8 4s2 looks like 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 4s2. Now, as cobalt is as carbonyl is a strong field ligand, so they are gonna get paired up. Correct? So as they are gonna get paired up, so they are gonna look like this. So guys, we have sp3 now. Sp3. So this is the trick question in ICO4. I have, while teaching you this segment, I have taught you that this is a trick question which is really something that people make mistakes in. Okay, so it's a tetrahedral structure and it is going to be exactly teachers. It's a tetrahedral structure and it's going to be your sp3 hybridized, not dsp2, whereas this guy would be dsp2. Okay, you can just solve this and you'll be finding this dsp2. Yeah, the previous question now, this one. Okay, guys, I got a request to solve this question, hybridization. So would you do it for me? Fe En whole twice Cl2, and then we have a Cl outside of it. Let's solve the hybridization. So first is definitely, you have to figure out the oxidation number of iron over here, which is +3. Correct? Now, iron in +3 oxidation state, how is it going to look like? 3d5, right? 3d6 4s2, from there it would be 3d5. So now in this situation, draw 5 electrons in here. 1, 2, 3, 4, 5. Now ethylene diamine being a strong field ligand, guys, you can definitely pair things up in here. So 1, 2, 3, 4, 5. Correct? And then you just put the rest of the electrons in here. D2sp3, exactly. Right. Yeah, the links of the of this notebook would be shared with you in the WhatsApp as well. Okay. Now, guys, I guess we are running a little late. I have to hurry up a little bit in order to teach you the most important question in DLF block. Now, guys, I told you, right, there's a PDF that I have made. I have really done a lot of homework for this. You can say I have looked into all the previous year question paper. I have looked into the board the mock paper that they have shared, and after that I have made all those questions. I have taken all those questions from different sources along with the answers. I have made the PDF of DNA block and coordination chemistry and organic chemistry as well. So I guess you have seen that one of the topics is ABCD type question. For that as well, I have made an entire PDF full of those blackboard questions along with the solution. That is also I'm going to share with all of you. For DNA block, I'm going to solve 1 or 2 questions in today's session, but guys, I'll be sending you the PDF along with the solution. Do check that PDF, and that is all you need for your board's preparation. There's nothing else needed other than that PDF, which is only containing 30 questions, guys. That much of time we can definitely give to this chapter, right? Now, about this question, you have literally noticed it, guys. There are many questions from are coming in DNA block, specifically from those reactions, right? And I have given you many shortcuts or many insights about how to deal with these reactions. Correct? So I have told you that whenever they are talking about acidic medium K2Cr2O7, that means Cr2O7 2 minus in acidic medium. So guys, tell me, what is the final product you are expecting to get? Acidic medium K2Cr2O7, what's the final product? Exactly. The final product is Cr3 plus. Very good, Shreya. So guys, for MnO4 minus, what is the final product in acidic medium? Mn2 plus, correct? And for Cr2O7, Cr3 plus, right? Now, this is getting reduced, right? Plus 6 to plus 3, this is getting reduced. So what would happen to H2S, guys? It would get oxidized. So tell me, what would happen to H2S then? So H2S get oxidized to what? Right now it is -2, so it would get oxidized to sulfur, which is 0. This much we can all understand, guys. This is not a very difficult job to do. This much, right? Clear, everyone? Now see here. Now you look at the options. Now see, Cr2SO4 whole thrice. When I'm talking about Cr2SO4 whole thrice, guys, chromium over here is +3 oxidation state. That is what we are expecting to happen. Now, if you look at the option 4 here chromium is in +2 oxidation state, which is never going to happen. So exactly option 4 is the right answer. You don't have to look into the rest of them. Simple. For MnO4 minus as well, look for Mn2 plus in acidic medium, MnO4 2 minus in basic medium, MnO2 in neutral medium. Right? These are the products with MnO4 minus. Okay. Let's go for the next question, guys. Be quick and try to answer this question then. Lanthanoid contraction. Where do we see lanthanoid contraction? In which two elements? The most? Very good. So 4D series elements and 5D series elements, right? So guys, I have like when you are going through this chapter, there are certain elements in both 4D and 5D that you have to remember. Those are the victims of lanthanoid contraction. Who are they? Zirconium, hafnium, molybdenum, tungsten, silver, gold. Okay, these three are the victims of lanthanoid contractions. Because of the lanthanoid contraction, they have similar sizes, similar ionization energies, everything are the same, right? And guys, if I ask you between zirconium and hafnium, who has greater size? See, this is another question that has been asked before. So many of you, I guess you know that as well. Between zirconium and hafnium has more size. It's like shorter. Zirconium is bigger than hafnium. Okay. Sir, Y and NB actinoid contraction. I didn't understand that. You meant lanthanoid contraction only, right, Parth? So actually what happens is, if you see where is yttrium, so yttrium is candium, yttrium, lanthanum, actin, right? And where is NB? So you have niobium and tantalum, right? So titanium, zirconium, hafnium, vanadium, niobium, tantalum. So Y and NB cannot, zirconium and NB are in the same series, right? There is no contraction or anything happening there, correct? So why did you write 3D next to? Very good, Devabrat. 5D. Okay. 5D, 5D. Exactly. Nice. That clear, guys? All clear? Great. Now, okay. Then again, guys, these kind of questions, be prepared for them. See, again, you have acidic medium. So MnO4 minus would turn into what? Mn2 plus. C2O4 2 minus. What is the oxidation state of carbon over here? +3. If it is getting oxidized, right? MnO4 has got reduced to become Mn2 plus. Now C2O4 is gonna get oxidized, right? So if it's gonna get oxidized, that means what would it form? Let's see how many of you know this. What would the C2O4 2 minus form, guys, after oxidation? Very good. Many of you got this correct. It would form CO2. CO2 over there, guys, carbon dioxide is the only element of carbon which has +4 oxidation state, right? Which we use on our, yeah. So it's having +4 oxidation state. So this guy is gonna get converted into CO2 here. Now you know both the products. Now you just balance this equation, right? Yes, perfect. Now again over here, Cr2O7 2 minus would turn into Cr3 plus. Then this would get oxidized to Fe3 plus. Now you remember the ion electron method balancing. That is how you have to balance both these equations. If you guys are struggling with ion electron method balancing, guys, go for a DRS session, and there will be you can just learn this topic one more time. And if you do that, I guess this compound and this relationship of this formula based questions would be, you'll be able to deal with them. It's not really that difficult. It's not something that you have to remember or mug up or anything like that. Okay. Exactly. It's very good. Okay. Now these three questions, I have selected them, guys, knowingly only, because all these three questions, they haven't came together. Okay, I have selected them, these three questions, separately actually. So if you see, the most important question over here is this guy. There occurs much more frequent metal bonding in compounds of heavy transition elements. 3D series, you have to explain this. Okay, so guys, if you see the boiling point or melting point, what do we call it? Graph, melting point graph. Over there, you'll be able to see the graph goes like this, something like this, right? Here in the bottommost position, you'll be having zinc, right? Here you'll be able to see. Who would I be able to see, guys? Very good, Tanvi. Very good, Nandita. The product for Cr2O7 in basic medium. That's a very good question, actually. Who asked this? Okay, say Ridwan. It's a very good question, actually. Guys, see, if you are treating Cr2O7, if you are treating Cr2O7 2 minus in basic medium, okay, it doesn't undergo any redox reaction. Okay, it turns into chromate ion, Cr4 2 minus. So the oxidation state remains just the same here, if you notice. Okay, it doesn't turn into any oxidation reduction reactions, guys. It just turns into chromate, CrO4 2 minus in basic medium, Cr2O7. Okay, so they won't give you Cr2O7 in basic medium. They would always give you Cr2O7 in acidic medium, because K2Cr2O7 is only an oxidizing agent under acidic medium. KMnO4 can act like an oxidizing agent under any medium, guys. Right? That's why KMnO4 is so famous actually. But K2Cr2O7 only in the acidic medium. Now, guys, in this bottom over here we have manganese, and in this top we have chromium. This question is often being asked: why do we see a dip in manganese? Over here also in rhenium also we see the same dip in the 4D transition series. So why do we see this? The logic behind this is, yes, very good. Yeah, very good, guys. So the logic behind this was, see, if you look at chromium, the number of unpaired electron over here is 6, right? It is 3d5 4s1. So the number of unpaired electron over here is 6. Now if you look at manganese, the number of unpaired electron over here is 5. Now they are going for this explanation, guys, that when you have more number of unpaired electrons, you can make more metal bonding. If you can make more metal bonding, that means you would be your melting point would be high. Okay, this question, instead of melting point, they have also asked this question with respect to enthalpy of atomization. Same question can be asked by the name of this terminology. Okay, enthalpy of atomization of manganese is lower than chromium. You're going to go for unpaired electrons. All right, guys, that was the number of actinide series exhibit a large number of the members of actinide series exhibit a large number of oxidation states corresponding to the lanthanoid series. What is the logic behind this, guys? See, when we are talking about lanthanoid series, we are talking about 4F, 5D, and 6S, right? But when we are talking about actinoid series, we are, what is actinoid written? Yeah. When we are talking about actinoid series, we are talking about 5F, 6D, 7S, correct? So far we are clear so far. By the way, make sure, guys, you know the electronic configuration of all the lanthanoids there. You are going to get questions from that. Okay, now should we remember all the Yes, beta. All the lanthanoids, not only the lanthanoids, but also their electronic configuration for each and every one of them. Okay. Specifically, praseodymium, then you have europium, then gadolinium, ytterbium, ytterbium, and this much is fine. If you go for praseodymium, na Tejas, cerium is compared, it's not showing any exception. Praseodymium is showing the exception. Okay. Cerium is not showing any exception. This is cerium, na? Praseodymium becomes 4F3, 5D06S2. So if you just go for praseodymium, cerium would be normally you would be able to remember. That's not going to be a problem for you. Okay. Now, like I was saying over here, guys. Now, so why do we see more number of large number of oxidation states in there? Because there is a rule, there's a theory called Bohr's correspondence principle, BCP, Bohr's correspondence principle. What does it say? It says that the more you increase the energy, yeah, it's like more you go higher up in the energy, the orbitals are kind of the difference between the orbitals are decreased. So more you go in the higher energy level, guys, what actually happens is your orbitals come closer and closer to themselves. As a result, the electrons donating ability increases. That means what I'm trying to say is in actinoids, 5F, 6D, 7S, all three of them are having so minute of energy difference that all three of them are acting like valence shells, and all three of them are capable of donating their electrons when it comes to the reactions. So as a result, guys, it can show large variety of oxidation states. That means, guys, if you go even beyond that, if you go to 6F, 7D, 8S, then you'll be getting even more number of varieties, because then the energy levels are almost same, right? So there'd be even more number of electrons that you can, share in the reaction. Are we clear so far? Right. Great. So now I'm going to, yeah. Is anybody asking any doubts or anything? No, right? Because small energy gap. Exactly. You can write this word Bohr's correspondence principle, but don't write it in Vaishnavi in the main, like main paragraph. Don't write it. What I used to do is I used to write it as a note. So under a segment, like first I used to write the entire answer. Then after writing the entire answer, I used to give some extra information. Like let's say this is my body of my answer. After writing the answer, I used to give like a note. Under that notes segment, I used to write all the extra information that I knew due to my JEE preparation. Okay, because some teachers are there, they don't like you writing things beyond the NCERT. They would find you like, they would look down upon you if you write more like that. And some teachers get impressed. So we don't know what's going to happen there, right? So we cannot take this chance. So that's why I don't write it in the main segment. I write it in a note, and I don't write much, guys. So also that's the same thing to you as well. Don't write unnecessary things. Always remember in JEE and NEET, you have been taught of different varieties of ways to solve a question. But it's your responsibility to know what all things that you can write and what all things you cannot write in books. So make sure, guys, you give some sort of times to do those things as well. All right. Okay. Right now, I'm going to keep this webinar to this. So up to this only. I've been showing you the kind of questions that can come, and I'm going to share these PDFs with you as well. Just go through those PDFs. You can understand. You would be able to, grasp this concept even better than this. I'm going to see you all today in the evening. Okay. Don't miss that session, guys. That in that session, I'm going to solve the ABCD kind of questions. That means, remember, they go like there is a molecule called molecular formula C8H9O, and that is reacting with something to give you A, and then that is reacting with another thing to give you B. Remember? So these kind of questions are being asked, right? For sure, they are going to be asked. If you just see the model paper that has NCERT has, CBSE has shared, they're giving 3 questions of this type in one paper. So you can understand that kind of questions are going to come. They're not going to ask you straightforward questions from the name reactions. So we're going to talk about that in the coming webinar. So Let's keep it up to this for today, guys. See you in the evening. Bye, everyone.
Thank you, sir. Bye,
You're
sir.
welcome, beta. Bye.
Sir, can you share this OneNote link?
Right. I'm gonna share this OneNote link with all of you over the WhatsApp right now. Okay.
Thank you, sir.
You're welcome, beta.